The first thing we'll discuss today are the properties of the real numbers. So in general, real numbers can be described as pretty much any number that you know of at this point in time. We're going to go into another set of numbers later in the year. But for now on, every number that you've learned to this point has been a real number. So things like the quarter, decimals, repeating decimals, radicals, and even pi, which is a non-repeating, non-terminating number. So a rational number is defined as basically anything that can be expressed as a fraction. So obviously 5/7. Any terminating decimal is always going to be a fraction, and any repeating decimal will always be a fraction. In terms of irrational numbers, we have radicals that don't terminate. So for instance, if I were to have a radical number like √4, that's equal to 2, and that's not irrational. All right, it's a number that neither terminates or repeats, and this terminates. Integers are basically your positive and negative counting numbers. Whole numbers are your counting numbers from 0 on to infinity. Your natural numbers are your counting numbers from 1 all the way out to infinity. So if we take a look at some of these things in the relationship to one another, the real numbers encompass every number you can think of. Your natural numbers are the smallest set, followed by the whole numbers, the integers, followed by your rational numbers, which we notate as Q in this case, and then your irrational numbers, which are the non-repeating, non-terminating decimals like pi and √3. So when we talk about algebraic expressions, we define an algebraic expression as any term or expression that contains at least one variable. So 2x we have here, 3x plus 2, 4x squared plus 3x plus 8. These all have at least one variable in them, some more than each other, and others have degrees and exponents, so on and so forth. If we want to evaluate an expression, it's as simple as basically substituting each value for each variable in this case. So we've got 4 for the x, we've got 1 for the y, that's going to get squared, plus 3 over negative, x is 4 again. I'm going to put this around here, square it, and 2 times that value of 1. And then we just go ahead and use our order of operations, which we haven't talked about yet, but we'll kind of imply that we've used them. We'll get to them in a minute. We do what's in the parentheses first, which is 5. That's squared plus 3 over. Now this is an exponent. We're going to do that first and then multiply it by a negative. So this is a negative 16. And this is a 2. Clean up the top. That's 25 and 3, which is 28. Clean up the bottom. That looks to be a negative 14, which ends up being negative 2. As far as the properties of real numbers, you got this probably somewhere in elementary school, maybe 7th grade, I'm not sure. But commutative properties basically state that you can add terms in any order. Likewise, for multiplication, the same thing stands. You can multiply things in any order. 5 times 3 is the same as 3 times 5, etc., etc. Associative property also works for both addition and multiplication. And associative property deals with a grouping, where this deals with an order. All right, and we notice that if we group the sum of 3 terms as the first 2 terms being added and then the third, that's going to give us the same thing as the first term added to the second 2 terms added first. An identity property is basically also called a zero property for addition, which means that if you add 0 to any number, you get that same number back. Likewise, it works for multiplication. You multiply 1 to any number and you get that number back. Additive inverse is basically adding the opposite. So in that case, you'll get a value of 0. For multiplication, it's the multiplicative inverse, which is also known as the reciprocal, where you take and multiply a term by its reciprocal and you get 1. Obviously, that term can't be 0 because if we were to divide by 0 in any case, we know that's an undefined answer. We don't really use closure too much, but I'll put it in anyways. If you add 2 real numbers, then their sum is a real number. You multiply 2 real numbers, their product is a real number as well. Distributive property means if you take a term multiplied by the sum of two terms, that's equivalent to the multiple of that term and its first term added to that first term and its product of the second term. All right. So now we've got an example where we need to fill in the blanks and basically say which properties are used to get from one step to another. So as you can see, here's my first term. My second term goes from this top guy to the bottom guy. The second one has remained the same, so I'm not even going to look at that. But I want to say what happens here. Well, it appears that this 2 has been distributed. So this is a distributive property. All right, now again, that second term remains the same in the third step, but I notice something's happened here, and the question is going to be, is the order changed or is the grouping changed? Well, like I said, that second term's still in the same spot. There's no new parentheses added. So this would have to be an order change. So this is a commutative. We'll just put an addition here because that's addition going on. And now we notice in this next term, everything's in the same order, but you notice the parentheses have moved from around the 2x plus 3 to the 2 and the negative 2x. So this is an associative property of addition. Order of operations, let's formalize this now. You've heard, I'm sure before, that's PEMDAS. Please excuse my dear Aunt Sally. You've heard of it a lot of different ways, I'm sure, but the order in which we want to do things are parentheses first, followed by exponents. Then, even though we have an m before a d in this PEMDAS notation, we're still going to multiply and divide. They're put at the same level, but you do them from left to right. Likewise, in addition and subtraction, which are the last steps you're going to do, you're going to do those as you see them from left to right. Let's do an example or two. So here's a situation where there's no parentheses. We just have to follow the order of operations. Since there's no parentheses, we look for any kind of exponent, which is here first. So I'm just going to take it one step at a time. We're going to leave the subtraction there because that doesn't say negative 6 squared. It says 6 squared. So that's 36 divided by 2. So now I'm going to group all my multiplications and divisions as I see them. So here's 1. That's an addition. That's a subtraction. Here's a division, and I'm going to do these from left to right. So this is an 8, a 3, and minus 18. Then I do my additions and subtractions as I see them from left to right. So that's 11 minus 18, which is negative 7. That should be done. In this next problem, we've got some parentheses in to start the problem off. In theory, this is a parentheses here, but it's by itself. It's not grouped with anything else. So that's just notating the negative 5 is separated, and it's not a subtraction. So I do what's in these parentheses first. We have 4 plus 2 times 6 minus, this is a multiplication. I'm going to do this first. 2 times negative 5, which is negative 10. And then I still have those parentheses to deal with. So I'm going to take and subtract 6 and negative 10. I have a 4. The 2 is still there. I'm going to keep this parentheses here. This goes to a 16 over 2 minus 7. Now you'll notice in this fraction, I've got to take and do this multiplication in the numerator first. So this is 4 plus 32 over 2 minus 7. And then we clean up the top. That's a 36 over 2 minus 7. I'll do the division first. 18 minus 7, which in our case is going to be 11. So properties of exponents. Now, the thing we've got to notice about this is all these x's in this case are what we call the base. And these properties are all going to be based on the fact that we have the same base throughout the entire process. So if we have the same base and two terms are multiplied by bases with different exponents, we take and add those exponents, keep the same base. Same base, and we have a division of two terms with exponents, then we subtract those two exponents, keep the same base. if we have a base raised to a power, but that term is raised to another power, keep the same base, multiply the two powers together. If I have a negative exponent, that's the same as taking the reciprocal of the term and changing the exponent from positive to negative, or from negative to positive, excuse me. Okay, likewise, we can express that as saying, well, that's whatever that fraction is to that power. And let's do a couple examples relating to that. So in this case, this is all multiplication. I can do it from left to right, one at a time, or I can just multiply everything across. So if I see I have a 4, a 3, and a negative 3, that's looking like negative 36. We said this was all multiplication, so I can add the numerators. Now keep in mind, numerator here is a 1, a 2, and a 3, so same base, x raised to the 6th. Y, that's a 1 is my exponent. And then here's another 1. So I have 1, 1, and 5, which makes y, same base, to the 7th. This is a little bit different. What I like to do is I like to deal with, just as the order of operations state, deal with the powers first. So we know this y has a singular power of 1, and so does this. So we'll take, and I'm just going to cube everything inside. So 4 cubed. That's 16 times 4, which I hope is still, what is 16 times 4? 64. And then we've got x. I'm going to raise a power to a power. So I'm going to multiply those. That's 15. Y to the 3rd. This is now multiplied by, we don't have any constant to worry about. So this is just x to the 12th and y to the 4th. We've turned this now into a product. So 64 times 1, there's no constant over here. It's an invisible 1. So that's a 64. I'm going to look for the same bases now. So x is a base, and I add the powers, which gets me a 27. And then y, add the powers to the 7th. All right. These next two are a little more involved. Again, this is a fraction. I'm just going to take and square everything inside. If you have another way to do it, you're more than welcome to. But this is a 9. That's an x squared. 25. Multiply the powers, y to the 4th. This is going to be multiplied. What I like to do on this is I'll just bring my negative exponent in first. I'll go x to the negative 9. 3 to the negative 3. Y to the negative 6th. So now what I'll do is I'll take, and any negative exponents I'll see, I'll move those, take the reciprocals of them. So whatever on bottom that's a negative exponent, move it to the top. Whatever on top that's a negative exponent, move it to the bottom. So there's 9x squared and 25y to the 4th remain in place. Everything here is going to move. So I have a 3 cubed on top, which is 27. I have y to the 6th on top. And then on the bottom, I have x to the 9th. So now, rules for multiplying fractions. If you can reduce, go ahead and reduce diagonally or on top of each other, which we can't in this case. Well, actually, we can for the variables, but I'll do that in the last step. So we're going to take 9, multiply that by 27, and let's see, 9 times 27 is going to be 243. Bring this down here to 43. And then I'm going to just keep the x squared here, the y to the 6th here, keep the 25 on the bottom, x to the 9th, and y to the 4th. Now, we've got a division here. Obviously, 243 and 25 don't reduce. But now I've got a situation where I have same base and 2 on top, 9 on bottom. I could do a subtraction of those and get a negative 7, but mathematicians typically don't like negative exponents in answers. So what I usually do is I'll say, hey, look for where you have the biggest power of x. So in this case, my biggest power of x is the 9. Subtract the 2, so I get a positive 7. 9 minus 2 is 7. And put the answer where that biggest base power was. So that's going to go on the bottom. And if you think about it, there's 2 x's on top and 9 x's on bottom, and you get a 1-for-1 reduction, which makes 7 x's left on the top, or on the bottom, sorry. And then lastly, we've got y to the 6th, y to the 4th, biggest term in the numerator, subtract the 2, get y squared. The biggest term is in the numerator, so we go y squared up here. Again, another way you can look at it, you could write out 6y's and 4y's, you get a 1-for-1 reduction, and there's 2y's left in the numerator, okay? This is the one most people have a tough time with because it looks so different. My base is no longer a variable, it's a number. But if we follow the rules, everything should go well. So I'm going to look, and this has an exponent, so I'll use that first. This is a 5 to the n minus 3. Now, in this case, it says if I have a base with a power raised to another power, I multiply the powers, which means I don't touch the base. So this 5 stays as is. Now I multiply the powers. That's 4n plus 8. That's what the rule tells me to do, over 5 to the n minus 4 power. Now, in the numerator, I have a multiplication of two terms with the same base. So again, I'm going to keep the base the same and then add the powers like the property tells me to. I've got 4n plus n is 5n, and 8 plus negative 3, or 8 minus 3, however you want to look at it, is 5. That's all over 5 to the n minus 4. Now in our final step, we have a division of two terms with the same base. I'm just going to take and do as they asked me to do and subtract the powers. I'm just going to write it out for funsies. We've got 5n plus 5 minus n minus 4. Right? And so in this case, 5n minus n is 4n, and 5 minus a negative 4 is like 5 plus 4, or 9. So that will be the solution there. So that's the end of the first day, and we will talk about more tomorrow.